Okay, so this is Chem 2 notes on concentration and rate. You have a packet, looks like this, and this is what we're going to be talking about today. Okay, so before we look too in depth at what's on the paper or what's on my board, which is just a copy of what's on the paper, this is a whole discussion on how we analyze reaction rate based on changing concentration. So somewhere up at the top of your paper, we're going to talk about studying rates while changing reactant concentrations. And that's the big idea behind this section. So we're going to be looking at what happens to the rate when we change the concentration of one reactant, but also what happens to the rate when we change the concentration of a second reactant, assuming that the reaction has more than one reactant. So, okay, you're going to get very used to looking at charts that look just like this, and they're going to well, first you're given a reaction, and that reaction is up on the top. It's written on your paper as well. And then you have this chart. And it has 4 experiments, and if you look closely, what they have done is they have taken the each reactant and changed its concentration, or in some places kept it the same, and analyzed what happened to the rate. So that goes back to what we talked about, that this is a discussion of studying the rate or studying the changes in rate based solely on changing reactant concentrations. And in this case, changing both NH4 plus's concentration and NO2 minus's concentration. Okay, so we're not going to get into anything in depth in this situation. I just wanted to draw your attention to a couple things. So let's talk about perhaps how NH4 plays a part in rate. So to do that, we would have to compare 2 experiments where NH4 was changing, but NO2 was not. And the reason we do that is because if we look at rates in 2 experiments where both concentrations are being changed, well then we don't know who's responsible for changing the rate. It's just like if you're trying to run an experiment about how plants grow, and you change the amount of water you give them, you change the amount of sunlight you give them, and you change the type of soil between a set of plants. Well, how do you know who was responsible for the growth? You don't. So this goes back to we always change one variable at a time. So in this case, if we want to look at how NH4 and how only NH4 affects the rate, then we must keep NO2's concentration constant between 2 experiments. So if that's the case, what 2 experiments make the most sense to look at? The answer would be 1 and 2. Why? Well, because if you look at 1 and 2, what happened to NH4's concentration? Well, it went from 0.01 to 0.02. That was, in effect, doubling. It doubled. Look at NO2's concentration. Nothing happened to it. So this guy doubled. Nothing happened to this. And what happened to your rate? Well, conveniently, the rate doubled. So doubling NH4 doubles the rate. Some kind of directly proportional relationship exists right there. But then there's a second question of, well, how does NO2's concentration, or how does changing NO2's concentration affect the rate? Or does it? So in this case, we would want to look at where does NO2 change, but NH4 stays constant. And conveniently here, that's experiment 3 and 4. So if you look at 3 and 4, NH4 stays the same. So that concentration doesn't change, and therefore we're not going to see an effect on the rate in that case. But going from 3 to 4, NO2's concentration doubles. And again, conveniently, look at what happens to the rate. It also doubles. So not only does NH4's concentration have some kind of directly proportional relationship to rate, so does NO2's. And we got all of that just by looking at this chart. And we're going to do that in much more detail later, and I'm also going to teach you how to approach this from a mathematical perspective, how to analyze how changing concentrations affect rates. That was just a very general overview. So if you wanted to summarize that, you could say there's that rate is proportional to both the concentration of NH4 plus and the concentration of NO2 minus. And that's effectively what we have gathered from looking at this chart. So remember in our first discussion, we talked about that changing reactant concentration should change rate, and if we increase it, the rate should increase, and that's true in this case. We're seeing a direct increase or a directly proportional increase in the rate and changing their concentrations. Okay, so now we're going to talk about something called rate laws. Okay, so this is a discussion that starts out a little bit strange, so you might have a lot of questions, and that's okay. Eventually, I will answer them. All right, so what's a rate law? I'm obviously shortcutting concentration and using my bracket symbols that we know mean concentration. Okay, so let's say we had, I guess a rate law is an expression that shows how the reaction rate depends on the concentration of the reactants. Maybe I should have added that. If you would like to change your definition, you can. Okay, how the reaction rate depends on the concentration of the reactants. So let's say we had a very general reaction that looks like this. Where capital A, B, D, and E are the chemical species, so, your reactants and your products, and lowercase a, B, D, and E are your coefficients, okay? So again, no chemicals involved here, just symbols to make this a little bit easier. Then in general, we can write this thing called a rate law, and it looks like this. All right, so it's the rate equal to K, it's a lowercase k, we'll come back and I'll explain all of what that is, times the concentration of reactant A, okay, that's this guy, raised to some power M, times the concentration of reactant B, raised to some power N. Okay, where M and N are whole numbers. But notice that I didn't raise A to lowercase a, nor did I raise B to lowercase b. That's because M and N come from something different than the balanced equation. Okay, M and N are not the coefficients, but they're called orders. Okay, they're actually called reaction orders. So we're going to get more into M and N and where they come from and what they mean later. All right, so you should have another question, which is, well, what's K? And K is something called a rate constant. Okay, and a rate constant is exactly what it sounds like. It's a constant for that reaction. Okay, so let me see how I want to summarize this. The rate constant, so K is a constant for a particular reaction at a specific temperature. So meaning if I have some reaction that runs at, let's say, 30 degrees Celsius, then K would be a constant value, and I would eventually be able to solve for K. But if I change the temperature of the reaction, K will change, and also if I change the reaction. So meaning if I start talking about a completely different reaction, well then K is no longer a constant because the reaction has changed. Okay, so let me erase this so I have some room, and then we'll talk about a specific example because hopefully you still have room on your paper. Okay, let's go back to the reaction that we started this discussion with, the one that's at the top of your paper. It looks like this. N2 plus 2H2O. Okay, so if that's the reaction, then what we can now do is write a general rate law for this. And it would look like this, just like what we just did. Except this time, I don't have reactants A and B, I have this reactant and this reactant. So I can get a little more specific in my writing of the rate law. And so it would look like this. Rate equals, remember, don't forget K, who's the rate constant. At this point, I don't know the rate constant, I don't have a number, so we just leave it as K. So this time it's going to be times the concentration of this reactant, NH4 plus, raised to the M, that's just the variable that I use, times the concentration of NO2 minus raised to the N. And that's the rate law. This rate here is called the rate law, and you're going to be writing lots of them in this chapter. Now, we have a lot of missing pieces to the puzzle, because see, what's cool about a rate law is it can be used to solve for an unknown missing part. Like perhaps we can solve for the rate, or we can solve for K. But right now, I have 4 unknowns, if you look closely. I don't know what this is, I don't know what this is, and I also don't know the values of M and N. So at this point, this rate law equation is kind of useless to us until we come up with more information. But this is all we could write as of right now for this reaction with a rate law. So it's always rate equals K, the rate constant, times, excuse me, the concentration of each reactant, and only the reactants, not the products, raised to some whole number power called orders that we'll talk about later how we find them. And there's Chester in the background. Okay. Going on, if we flip to the next page, we're going to get into a little bit of a discussion of the exponents or the orders in the rate law. All right. So, let me erase and okay. Let's see, what's the best way for me to do this? Okay, let's that's Chester ringing the Christmas decoration on my door to come inside. Okay, let me make up something for you, and we will use it as a general discussion. All right, let's say we have some reaction, and we wrote a rate law, and let's say it looks like this. Okay, so I'll give you a minute to write that. Okay, so first of all, we have now learned the name for these. Do you remember what they are? They're called orders, and they must be determined experimentally or with a series of data, which is what we will use. Okay, we'll use the table like we looked at on the very front page at the beginning of this discussion. So those are orders, and they must be determined experimentally. They do not come from the balanced equation. So if you've picked up nothing else that I've said today, please remember that those orders do not come from your coefficients. Coefficients tell us so much, but in this case, they have nothing to do with the orders in a rate law. Okay, so we can talk about this reaction in a couple ways, okay? So we can say that this reaction, whatever it might be, is second order with respect to reactant A. And I got that because the 2 on the A is second order. Now I could also say that the reaction is second order with respect to B. And I got that from the 2 on B's concentration. But the third way I can discuss the reaction order is something called the overall. And if you had to guess, I'm sure you could guess what overall reaction order means. It's the sum of all the orders. So meaning it's a combination of the second order here and the second order here to give us 2 plus 2, of course, is 4. And so we could also discuss that this is fourth order overall. So all 3 of those ways are correct in discussing the reaction. So you could say it's second order in A, you can say it's second order in B, but you can also say it's overall a fourth order reaction because you have summed those exponents. Okay, so now let's switch gears just for a minute and talk about what those exponents really mean. Okay, so I'm going to start to make up some little simple rate laws, and then we'll talk about their exponents. Okay, and you might run out of room in this section, and if you do, I would just get another sheet of paper out because this is too good of a discussion and too good of examples not to write down because you've run out of room. Well, that's probably my fault for not giving you enough room. So this is kind of your warning. If you need a separate sheet of paper, get one out so that we can continue this and you don't run out of room. Okay, let's say this is the rate law. And you have some reactant A and the order is 0. Well, what does that mean? So what's really cool about this is we can kind of play a numbers game and we can talk about, well, if I change the concentration of A, what happens to the rate? Remember, that's the name of the game. If I change this, what happens to this? What's the relationship? Okay, so what's really cool is we can make stuff up. I always pick really easy numbers. So let's just pretend that A's concentration is 1. Okay, so 1 to the 0 times K equals what kind of rate? Well, here's what we're going to start doing. We're going to start dropping K out of here because K is just going to be some number and it's not really going to influence our results here. So I'm just going to drop K out. Okay, so what's 1 to the 0 power? Well, anything to the 0 power is actually 1. I don't know how many of you knew that, but if you didn't know that, you can always check it on a calculator. Okay, so now let's pick something easy, like what happens if we double the concentration? So my concentration was 1. If we're going to double it, let's make it a 2. Remember, this doesn't change because that's what we're studying. Well, what's 2 to the 0? Conveniently, it's 1. So in this case, we tried to investigate this relationship by doubling the concentration, and look what happened to the rate. Nothing. Okay, there was no change in the rate. So when the exponent is a 0, okay, when the exponent is a 0, and only when the exponent is a 0, changing concentration has no effect on the rate. Sorry, my letters got all scrunched. So when the exponent is a 0, changing the concentration of A, we could increase this by 100 times and make this 100. And 100 to the 0 power is still 1. And so we could change the concentration of A all day long and nothing would happen to the rate, because in this case, the exponent is a 0. Okay, so let's keep going up here. Let's say now we have some reaction where the exponent is 1. Now, you're not going to see them right in a 1 because a 1 is understood. Just like in the, the expression x plus 2, it's understood to be 1x plus 2. So that's really a 1. If you feel better writing it as a 1 for now, you can, but it's not going to be written like that in reality. Okay, so again, let's play the numbers game. Let's say A's concentration is 1. 1, I'm just making that number up. See, you can make up any number. I just like to pick very simple numbers. So I made up this. 1 to the first power is what? Well, 1 to the 1 is 1. Okay, so now let's double this again. So if I double it, I would make it a 2. And in this case, it's 2 to the first. Well, 2 to the first is 2. So look what happened. Your concentration, we doubled. Your rate, we also doubled. So this is the one where whatever you do to A happens to the rate. This is the directly proportional relationship. So I could prove this to you, but I'll just talk about a couple examples. So let's say this is still the rate law, and instead of doubling, let's say we quadrupled A's concentration. Well, as long as this is still my rate law and my exponent is still a 1, whatever you do to the rate, whatever you do to A will happen to the rate. So if I quadruple A, my rate quadruples. What if I half A? Well, whatever I do to A will happen to my rate. So if I half A, my rate will also be cut in half. And look, I can prove it to you. It's easier if you pick easy numbers, but let's do it. I'll do it with one where it's not doubling. Again, you don't have to write this if you just want to see another example. Let's say A is 6. 6 to the first power, well, that's just 6. And let's cut it in half. Let's divide it by 2. And that makes us a 3. And 3 to the first is a 3. So what happened here? Well, it got divided by 2. What happened here? It also got divided by 2. Proportional relationship, no matter what you do, if the exponent is 1. First order. Okay, let's do a couple more where we change the exponent and get a little bit higher in our numbers. Let's talk about what happens if the exponent is a 2. Okay, again, let's pick some numbers. Let's make a 1. Okay, so it's 1 squared. Well, that's just 1. Now let's double it. 1 becomes a 2, 2 squared becomes a 4. So in this case, notice, it's no longer directly proportional. So this one doubled, this one quadrupled. These ones are related to the squaring of what you do to the rate. So, sorry, I misspoke again. The squaring of what you do to the concentration. So, second example, something like, let me think about it. Let's say this was a 1. Okay, and let's say I triple it. Well, if I triple that, that becomes a 3. and 3 squared becomes a 9. So see, I said it was related to what you do squared. So we tripled, 3 squared is 9. And so again, here we have a multiplied by 3 situation, and over here we increased by a factor of 9. Okay, so no longer directly proportional, because now we're increasing by the square of how much we have changed our concentration. And then we can do one more. Let's do, what if A was a 3? Again, let's make this 1. 1 cubed is 1. Let's double it. So 2 cubed, be careful, that's not 6. 2 times 2 times 2, so that's 8. So what happened? Here we doubled, here we increased by a factor of 8. So now we're increasing on a cubic level because of the 3. So that's how orders can affect reaction rate. Okay, so there are a couple of practice problems on your paper if you would take a minute and answer those. And then we will continue. Okay, so let's see. The experimentally determined rate law for a reaction is given. What are the reaction orders in this rate law? Well, I think you could say a couple things. Any of these would be acceptable. You could say that it's second order in NO. You could say it's first order in H2. Or you could also say that it's third order overall from adding the 2 and the 1 together. Both of those are acceptable. And B, does doubling the concentration of NO have the same effect on the rate as doubling H2? The short answer is no, because their exponents are different. So because their orders are different, doubling both will cause different changes to the rate. The longer answer would be, well, doubling H2's, who has an order of 1, would double the rate. But doubling NO's, who's being raised to the second power, would effectively square the doubling, which would quadruple the rate. So that would be the long answer. Short answer being no, because their exponents are different. Okay, so continuing down your page, we are now on units of the rate constant. And so this is a little bit of an interesting discussion. And again, the rate constant is K. We don't know how to solve for K yet. That's okay. We're learning this kind of piece by piece. But what's important here are units. And the fact that the units of K are not always constant, because they depend on the overall reaction order. So again, I'm going to make some stuff up. We're going to solve for the units of K and discuss it. All right, so let's say I have this reaction. And we are interested in K. So not numerically speaking, only units. So if we were to solve this for K, I would divide both sides by A and B, and I would end up with this. K equals rate over concentration of A times concentration of B. All right, so for our purposes, rate is going to be measured in molarity per second. Okay. Again, it can be measured in other units, but most of the time you'll find it measured in molarity per second. Okay, so that's just the top. That's the unit for rate. Well, then what's the concentration of A going to be measured in? It's most definitely going to be measured in molarity because it's a concentration. And then the concentration of B will also be measured in molarity. So essentially what we have is molarity per second divided by molarity squared. So how do we reduce this? And man, this is just a mess. So technically, if you put this over 1, you have 2 fractions. And you should know how to divide fractions. That's a very simple algebraic operation. And that is by multiplying by the reciprocal. So if you look, you would take this and you would flip it to make your reciprocal. So 1 over m times m. And now notice, does anything cancel? Well, one of these cancels with one of these. And what do we have left? We have 1 over s times m. Okay, which is a perfectly acceptable unit for K. The other way to write that, though, I'm not sure if you guys are familiar with this, you should be, because most of you are in upper level math, is to bring those units to the top of the fraction, to the numerator. But by doing that, you make their exponents, which are technically right now 1s, negative. So technically, that's the same thing as s to the negative 1 times m to the negative 1. So those are the units for K if the reaction is second order overall. So we're going to keep a theme going because I'm hoping that you see a pattern. All right, it's okay if you don't see anything yet. Let's make up another one. Let's say this time we have this. So first of all, overall reaction order is 3. I should have done that over here. Overall reaction order was 2. Okay, we're getting the 3 from the 2 and the 1. All right, again, let's solve this for K. Take A and B to the other side by dividing. Don't drop your exponents. Okay, again, rate's going to be measured in molarity per second. A is going to be measured in molarity. B is going to be measured in molarity, but B is squared, so it's going to be molarity squared. Again, it's pretty ugly, so if we want to deal with this in fraction terminology, it would look like molarity per second times, flip it, 1 over m times m squared, okay, which is essentially m to the third, but actually it's written nicely so that this cancels. And what you're left with is 1 over s times m to the second, or s to the negative 1, m to the negative 2. So, again, maybe you don't see a pattern yet. We're going to do one more. And I'm gonna summarize my results up there in the top because I have to erase them. I'm out of room. Okay, so let's see. Let's summarize. When it was second overall, K was s to the negative 1, m to the negative 1. When it was third overall, K was s to the negative 1, m to the negative 2. Let's do fourth. Any guesses? You might be able to guess. Okay, so let's make something up. Fourth overall, how about a to the second and b to the second? Right? Move my board. It's hard for me to reach. Okay, so solve for K. Take a and b to the other side by dividing. Oh my goodness, did it again. Molarity per second over molarity squared times molarity squared, which is essentially molarity to the fourth, which is molarity per second times 1 over molarity to the fourth. So one of these cancels with one of these, making that a 3. And now we have s 1 over s times m to the third, or s to the negative 1, m to the negative 3. So here is the pattern so far. Do you see it? Well, look at the exponents. It's a very simple pattern. Now, I know they're negative, but kind of take the absolute value. I have a 1 and a 1 adds up to 2. I have a 1 and a 2 adds up to 3. I have a 1 and a 3 adds up to 4. So if we had to guess what fifth overall would be, notice that S hasn't changed. S is always going to be to the negative 1, and M has to be whatever added to the 1 makes the overall. So in this case, it would be to the negative 4. And you can use this to shortcut your units for K. Otherwise, you'd have to do it mathematically every single time, and that can get kind of cumbersome. But you can use this method to shortcut units for K. So there's a practice problem. Solve that for me real quick, and we will go over it in just a minute. Okay, so it says for a reaction with this rate law, determine the units of K. So again, we want K by itself, so we would divide by this on both sides. We end up with this. Rate, always measured in molarity per second. This guy, just going to be measured in molarity. Again, if you want to think about it in fractions, molarity per second times, flip it, 1 over molarity, cancel, cancel, you're left with 1 over seconds, or seconds to the negative 1. And look, that actually fits. If you go up here, oh, can you see it? Yeah. So my first overall would be up here where I don't have any room. And remember, the S has to be a 1, and you have to add it to the M to get the first overall. Well, 1 plus 0 gives me first overall. And M is has an order of 0, has an exponent of 0. So therefore, I don't have to include it. So in this case, K would have units of S to the negative first, or you can say 1 over S, whichever method you prefer.